All right. Hello and good morning for the last time. This is our last scheduled lecture class. So that's... Whoa, why is this so loud? Hang on. Hello, 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 hello. Hello, hello, hello. Give me 1 second. Hello, 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 hello. Hello, hello. Hello, hello, hello. Whoa, 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 that's louder. There we go. Hello. Okay, I think that's... Oh, hello? All right. Bup, 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 bup. Hello, 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 hello. Okay, sorry. Sorry for all those hellos. Hello. Yes, I do. I do. Someone messed with my mic settings, probably inadvertently, but it was sounding super... Whoa. Whoa, that is deep. This is our last lecture. We still have office hours on Friday. So that's still going down, but this is our last official class. This is also your last time to get at me with questions about the exam. As you all know, everything opens up at 3. I finished setting up the emails to go out at 3 p.m. Today. Contact me if that's not happening, and the multiple choice will also go live. And you know what? While we're doing this, it'll most likely be the longest office hours ever. And I am totally down. So today with lecture, I am here to answer your questions. Anything you guys want to talk about, we can get into. What I'm doing right now, I had this thought to do this earlier, and then I promptly forgot. I am going to, right now, let's see, get a copy of the cover page up onto, I almost said Netflix, up onto Canvas, and that way everyone will have Canvas exam. Then here is exactly how those will go down. I'm actually going to pull up my periodic table real quick. All right, so on Canvas, for VSEPR and hybridization, the way this will go down is I will give you a Lewis structure, and I'll give you... So I will give you... oh, you know what? Okay, Wi-Fi. Okay, that's good. Okay. It's showing. Okay. All right, let's hopefully one of these things on the Canvas exam. And in the context of Canvas, I would give you, different options. But here, what we're going to do is we're going to label each, and because that's how you would determine what the correct answer is. So first off, when you look at your central atom here, we have 3 atoms. We have 3 atoms, 1 lone pair. So that means we have 4 electron groups. All right. The number of electron groups determines the electronic geometry, which for 4 electron groups is tetrahedral, and the electronic geometry determines the hybridization. So if we have 4 electron groups, that means we need to use 4 orbitals in our hybridization scheme. So the hybridization here will be sp3. All right. Now the molecular geometry is based on the electronic geometry, but we have to take into account that we have lone pairs here. All right. So when you have a tetrahedral electronic geometry with 1 lone pair, your molecular geometry is trigonal pyramidal. All right, and then again, the bond angle will be based off of the the bond angle will be based off the electronic geometry, tetrahedron, but the presence of 1 lone pair changes the bond angle again. Instead of a pure 109 degrees, it gets pinched down to 107 by the presence of that 1 lone pair. This would be the correct answer if I asked you for the molecular geometry, the correct answer for the bond angle, and the correct answer for the hybridization on the Canvas exam. The only difference is that on the Canvas exam, it would be I would give you it's multiple choice, so you'd have several options to choose from, and you'd have to identify the correct answer. So that's how molecular geometry, bond angle, and hybridization would be tested for on the multiple choice exam. Okay, Sulai, excellent question. So, oops, hang on. That's Sulai. So in a pure tetrahedron, yes, exactly. The bond angle is 109. But exactly. But the lone pair creates more electron-electron repulsion because those lone pair electrons are not being shared. So the lone pair kind of pushes down on the bond angles, constricts them a little bit. It reduces the bond angle by 2. So it's that lone pair on top that kind of pinches it down to 107. Totally. All right. Lame. All right, so that is how you would see VSEPR or hybridization tested for with the let me see, with electron configurations. So for electron configurations on the Canvas exam, so there's two ways. I will give you one of two things. I will give you the electron configuration, and you'll have to find the atom or element. Or I will give you the element, and you will have to find or identify the correct electron configuration. So, for example, let's say I gave you the following electron configuration. All right, let's say I gave you this. Kr, 5s2, 4d, 8. You need to take this electron configuration and find what atom. And again, on the yep, these are all multiple choice. Yeah, so Sule, so on Canvas, everything is multiple choice. So you will never, you'll never have to, yep, Raj, that is on point correct. So yeah, so if on the Canvas exam, Sulai, everything's multiple choice. So I'll give you this electron configuration, then you have to identify the correct element. But the way you do that is, okay, we got to start with krypton, right? We got to start with krypton, and then we're going to count over 1, 2 spaces into the 5s block. Then we're going to switch it up and go 1, 2, 3, 4, 5, 6, 7, and 8 into the 5D block. So the correct answer that you'd select out of the multiple choices would be palladium. Yeah, it's the third exam is the easiest, Sula. You're totally right. Jesse, so the ground state doesn't include d orbitals if they aren't valence electrons. Okay. So Jesse, when you are writing ground state electron configurations, you want to include all electrons with a higher energy than the valence electrons of the noble gas used in the abbreviation. All right. So, Jesse, you want to do all of the electrons that are on a higher energy than the noble gas used for the abbreviation. So they're not necessarily valence in the sense of the highest energy orbital, because as you can see, here we have 5s followed by 4d, and 4d is has a lower principal quantum number, but they are valence in the sense that they're the group of highest energy electrons. All these electrons are at a higher energy than the valence electrons for our noble gas krypton. So everything that comes after krypton will be included in the electron configuration. The other way that you'll see this on the Canvas exam is I could give you an element like samarium. Whoa. So I could give you an element like samarium and ask you to find its electron configuration. And again, I'll give you multiple choice answers. Will I ever give the full electron configuration? Great question, Raj. On this test, I always use the noble gas abbreviation. Yep, always shorthands. Because life is too short to write full electron configurations. All right, here, if I'm asking you to find samarium, samarium is in the F block, all right? And you know that first level of the F block sandwiches in between lanthanum and hafnium. All right, so here we're dealing with the 4F, which would make this the 5D, which would make this the 6S, which makes xenon our nearest noble gas with fewer electrons. So this would be xenon 6s2, right? Because you bounce 2 spaces into the 6s block. You bounce 1 space into the 5d, and then 1, 2, 3, 4, 5 spaces into the 4f. So 4f, 5. This would be the correct answer that you'd select if I gave you the atom samarium. All right, question. Will there be problems finding NL, M sub L, M sub S? Can you do an example of finding all the quantum number parameters? Yes, I can. So with quantum numbers, so here's how. Actually, let me bring my periodic table back. All right, so for quantum numbers, here's how this will go down. Let's see. Is it just me, or is anyone else stuck on the Lewis structure hybridization problem on the lab exam? Oh, I can't comment on that. Let's see. A, B, C, D. Well, let's just throw in an E for funsies. All right, let's see. Okay, Sulai, let's see. When D is 4 or 9, we take the S Sule, that is absolutely correct. Sorry, I just now saw your question. And Vraj, that is also spot on. Also spot on. Okay, Diana, this is getting back to your question. How will these quantum numbers manifest? On the multiple choice exam, I will ask you the following. I'll ask you to identify the set of quantum numbers that represent an electron in the blank orbital of a blank atom. All right, and the orbital and atom will change every time, but the question remains the same. So, for example, I could ask you to identify the set of quantum numbers that represent an electron in the p orbital of a argon atom. All right. All of the multiple choice quantum number questions on the exam will be worded just like this, and they'll switch out the orbital and the atom type. Other than that, they're identical. All right. And so then you'll have a set of quantum numbers. So I'll give you N. I'll give you L. I'll give you M sub L. And I will give you M sub S. All right. And then these will be, all different. So here I'm cooking up a problem. And then all right. So here's a string of possible answers. All right. And okay, so Vraj, let me see. I'm just seeing your questions just now. Highest period is the highest N value. Okay. Yep. This is totally process of elimination. All right, and then how do you do M sub S? Okay, so remember that, so first, let me add Vraj. M sub S only has two allowed values. It's either positive 1/2 or negative 1/2. Any value other than positive or negative 1/2 is not allowed. So that's an easy way to weed out wrong answers. All right. So if L equals 2, okay, Diana, I'm looking at your question. So if L equals 2 for M sub L, is there an actual precise value or is it a range? Okay, right. So Diana, the thing to remember is that M sub L is any integer from negative L to 0 to positive L. So if L equals 2, then the allowed values for M sub L can be -2, -1, 0, +1, or +2. Any of those are allowed. All right, so Vraj, the plus or minus represents whether the electron is spin up or spin down. But it doesn't matter which. It can be either positive or negative. Let's see, if you have two options left, M sub S is different. How do you know which one is right? Okay, so, Vraj, great question. If you have narrowed your answer down to two options, if you've narrowed your answer down to two options, and the only difference is in M sub S, one of them will have a value for M sub S that does not equal +1/2 or -1/2. All right. So if it's hinging on M sub S, then your correct answer will have one of them will not be equal to positive or -1/2. Okay, Sulai, the answer is E. Okay, let's see. Okay, Sulai, let me get back to you in 1 second. Winnie, that is correct. All right, so let's do this problem. All right, first order of business is check out the p orbital. All right, that tells you that your values for L has to be 1, right? Remember that L, when L is 0, then your orbital Sorry, let me just scoot this over. When L is 0, your orbital is S. When L is 1, your orbital is P. 2 is D. 3 is F. All right, so the fact that we have our L is 1 means that this, or the fact that we're in a p orbital means that L must be equal to 1. So instantly I find all of the possible answers who has a value for L equals 1, and I X out everything else. All right. So we've just pared this down from 5 possible answers to 2 because there's only 2 sets of electrons with p orbitals. Next, let's look at our atom. Here we're dealing with argon. All right. Argon is right here. And in the full electron configuration, argon has, so again, I'm just writing out the full. All right, that's the electron configuration for argon. And you'll notice that argon has electrons in p orbitals on the second level and the third level, right? It's got 2p electrons and 3p electrons. So based on the principal quantum number, both of these are legit. Both of these could potentially be an answer. Now let's look at EMSEVEL. When you compare these two, there's a problem with answer A's EMSEVEL. EMSEVEL ranges from negative L to 0 to positive L. So the largest possible value for EMSEVEL when L is equal to 1 is a positive 1. So this is not an allowed value for EMSEVEL. So this is how we discount A, and that tells us that the correct answer is E. Well, so yeah, Vraj, in most cases you won't have to worry about M sub S. Every once in a while you'll have to, but it's just knowing, is it positive 1/2 or negative 1/2? And if it's one of those, it's good. If it's not, then it's wrong. All right, so Sulai, circling back around. You nailed it. Nailed it way ahead of the rest of us. Do you want to do another quantum problem? Vraj, there will totally be boiling in. Yes. At Vraj and Winnie. There will totally be boiling point, melting point, freezing point problems. Jesse, EMSEVEL is how many orbitals of the type there are? Yes, Jesse, absolutely. All right, Sula, you want to see another one? Let's take another one for a spin. All right, so here, let's see. Let's do a set of quantum numbers that represent an electron in, how about, whoa, nope. Let's open a new slide. An electron in the d orbital of a cadmium atom. All right, so let's do how about that? And then we'll do and then how about Let's get some M-Savels in here. All right. Okay, let's see. Yes, totally. Okay. All right, so again, first step is let's look at the d orbital. All right. We need L is equal to 2. So I find all of my L's equal to 2, and I X out everything else. All right. We're down to 2 options. All right. Now we're dealing with a cadmium atom. All right. When we find that on the periodic table, you can see that it's down 1, 2, 3, 4. It's on the 5th period, right? But remember that you go from 5s to 4d. You drop your d orbitals down a level. So when I compare my principal quantum numbers here, I don't even have to look at m sub L or m sub S, because cadmium has no d electrons on the 5th energy level, only on the 4th. And so based on principal quantum number alone, I can rule out A and select C is my correct answer. Totally. So it's, and this is, okay, so this is a trick, actually. It's on the 5th period, but its d orbitals are 1 energy level down. So C, yep. C is the answer. It was C. And Vraj, you can be C too. Do you guys want to see another one of these dudes? Oh man, you can. The power is yours. If you don't believe me, look at these koalas. Oh, yeah. No. Diana, these are totally process of elimination. All right, like a hard one, a tricky one. Okay, let me see if I can cook one up. Though honestly, oh, that's thoughts. These two examples are exam caliber. Okay, so let me try to make the worst version of this that I can. How about this? First I gotta pick something. All right, let's pick an f orbital on a Burger King atom. I'm sorry, on a berkelium atom. So okay. Okay, yep. Okay. Tricky melting point, freezing point, boiling point problem. Dang, we can totally cook one of those up. Or at least I can try. We'll see if it's tricky or not. But let's do this one first, and then I'll shift gears. Okay, so let's see. All right, and what if we do... All right. Oh! Winnie, I will help you. Berkelium is right here. Boxed in green, number 97. Yeah. This is not 58. This is old 97. So, let's do this problem. First, we need to look at our orbital. We're dealing with L equals 3. And look at this. I've been such a turd. L equals 3 in all of these. Identifying the orbital didn't help us at all in this one. Let's look at where berkelium comes from. All right. Berkelium, as we've said, is number 97. And that second row of the F block links in right here on the D block. So if we look at the period, it is 1, 2, 3, 4, 5, 6, 7th period. All right. Almost all the way down. Now, here's the thing we've got to remember. We know that when you move from the 7s to the D block, you drop a level. So it'll be 7s, 6d. But then when you move from the D to the F block, if it's 6d, it'll be 5f. It drops down a step. All right. Now, berkelium has 5f. So first off, for this atom, all right, it has a radon core. If you look at the electron configuration, it'd be 7s2, 6d10. No, sorry, 6d1. 5 F 1, 2, 3, 4, 5, 6, 7, 8. 5 F 8. The problem is when you look at radon, right? We know berkelium has all the electrons of radon. Radon has the following electron configuration. So berkelium, because it has all the electrons of radon, has both 5f electrons and 4f electrons. So far, choice A and C are both on the table. We can rule out the 6th energy, the 7th energy electrons, but C is on the table and A is on the table. When you move to their M sub L's, both M sub L's are consistent, and now this is where M sub S comes in. You'll notice that A has an M sub S value that is not allowed, which means that C is our correct answer. Totally. So this one, yep, totally, Raj. This is an example where M sub S was the deciding factor. N was fine, L was fine, M sub L was fine, M sub S was how we had to determine which one was right and which one was wrong, because A had a value for m sub s that was not allowed. Okay, let's see. Wow, I missed a bunch of comments. It is not DK, it is BK. All right, let's see. DK for Donkey Kong. BK for Burger King. Let's see. All right. Okay. So I believe above. Yeah. Berkelium was Sulai. Berkelium was named after, Berkeley. Totally. Cause it was discovered there, as was Californium CF or, cluster or something. I like thinking of alternate names. I think it makes it fun. Okay, anyways. Let's see. Someone asked... Okay, Diana said, you'd love a tricky melting point, freezing point, boiling point problem. We can do that. All right. So let's take a look. Oh, I'm going to get rid of my periodic table. Berkeley is... Oh, man. Dude, I know. Actually, my brother is transferred to Berkeley, and this is his last semester of his senior year, which went all online. So it's a kind of a weird place to end it. But obviously, they can't have commencement during quarantine conditions. So some UC Berkeley students made an exact scale replica of the campus on a Minecraft server, and they named it Blockly. And they're actually going to be holding a commencement on their server. They sent out an invite to everybody who is a Berkeley student to attend. So we're going to be attending his commencement on Minecraft, which will be fun. I think it's either this Saturday or next Saturday, but we're looking forward to it. Okay. Let's see. Can you do each? Okay. So let me tell you my intermolecular forces secret. I wasn't going to tell anyone this. and here's the secret. And don't tell anyone else this. But the strongest intermolecular forces means that you'll have the highest boiling point, because it'll take the most energy to do that phase transition. Now, if you have the strongest intermolecular forces, you will have the highest melting point. And get this, if you have the strongest intermolecular forces, you will have the highest freezing point. So here's my secret. Boiling point versus melting point versus freezing point Doesn't matter. It's the same every time. All right. So Raj, your question, the question that you had, where was it? Yeah, highest everything point. Can I do a melting point problem, a freezing point problem, and a boiling point problem? They are literally all the same. So the answer is no, but when I do one, I am doing all of them. Lowest intermolecular forces means higher vapor pressure. Let me think about that one, Sulai. Yes. Sulai, that is correct. Because lower boiling points equals higher vapor pressure. But I made a promise to only test on boiling point, melting point, and freezing point. And so my dark secret that I will never tell anyone, unless you happen to be watching this video, is that the boiling point, melting point, freezing point thing is artificial. I'm just doing it to make it seem like the problems are different, but they're not really. What's the hardest and trickiest of all the questions for ever? Oh, for hardest of all questions ever for melting point, boiling point, freezing point. Well, Raj, it kind of comes down to this. I'll give you 4 compounds, and I'll ask you to rank them from the lowest melting point to the highest melting point, lowest to highest. And then I give you 4 molecules, and you got to do it. And it's not really that gnarly. Let me pick some. So how about this? Oh, okay. I will get tricky. Okay, so do it for these. So there's 1. Wait, no, I don't want oxygen. Give me a second. How about this? Oh man, Diana, you killed me. Trixie Hobbitses. I can be tricksy and I can be false. Here, I'll do this one. Oh, whoa, too many electrons on oxygen. Let's fix that up. All right, and then how about this one? And let's see, one last. one last hurrah. Here we go. All right. So let's do these. Let's rank these from highest to lowest melting points, or sorry, lowest to highest melting points. To do that, we need to determine what intermolecular forces we have at play. All right. So to determine our intermolecular forces, first thing that you want to do is London dispersion everything. Everything has London dispersion. All right, that's step number one. Step number two, after this, can we do a problem with how you would present the best resonance structure? Yep, Jesse, absolutely. Totally will. All right, so let's see. So we've got London dispersion on everything. Now to look at whether or not we have a dipole, we have to look at our electronegativity numbers. And sulfur has an electronegativity of 2.5. Hydrogen's 2.1. I'm just going to write these all up. 3.5 for oxygen. 2.1 for hydrogen, chlorine's 3.0, and arsenic is 2.0. All right, so when you look at your electronegativity differences for sulfur and hydrogen, it's 0.4. All right. This is nonpolar. Nonpolar bonds. All right. The question is, can it hydrogen bond? All right. Can it hydrogen bond? And when we're talking about hydrogen bonding, it has a lone pair, which is good, but there's no H on nitrogen, oxygen, fluorine, or chlorine, so no hydrogen bonding is present. Our first atom just has London dispersion. For our second one, if you look at the difference in electronegativity, it's 1.0, which means that we do have polar bonds, but there's no dipole-dipole because of symmetry, right? Our central sulfur is a tetrahedron, and we have 1, 2, 3, 4 oxygens. We have the same atom at every position, so there's no hydrogen bonding. No dipole-dipole, because they all cancel out for symmetry. Winnie, yes, I totally do. And actually, here, let me Chem 400. I am. Winnie, I'm going to upload the cover sheet to the test really quick. images. Upload. There we go. Whitney, I just uploaded the cover sheet to Canvas, so you'll be able to find the exam 3 cover sheet. Okay, so no dipole, no hydrogen bonding because we don't have any H's, right? So there's no H on nitrogen, oxygen, fluorine, or chlorine. Second one, we have an electronegativity difference of 1.4. So we have polar bonds. We don't have to worry about symmetry here, so we do have dipole, because again, here we have a tetrahedron, but we have 1, 2, 3, 4 positions. We don't have 4 H's on every position. So we do have dipole, and we have hydrogen bonds, right? We have lone pairs and a hydrogen on oxygen. For our final example, our final contender, we have, let's see, an electronegativity difference of 1.0. So we have polar bonds. We have polar bonds, and you'll notice that we don't have symmetry here because we have 1, 2, 3, 4 electron groups around our central atom. If we had 4 chlorines, we wouldn't have dipole because of symmetry, but we do. We have no hydrogen bonding because there's no hydrogens here. All right, so let me label these. I'm going to label this. Oops. A, B, C, and D. All right. So if we're going to rank these from lowest melting point to highest, all right, the highest will definitely be, I almost said oxygen, water, right, because it has hydrogen bonding. Second highest will be D because it has dipole. Now, when it comes to A versus B, all right, remember, larger atoms results in stronger London dispersion forces. A has sulfur, which is pretty large, but H's, which are small. B has sulfur and oxygens. Because oxygens are bigger than sulfur, they will have larger, or I should say stronger London dispersion forces at play. So B will be third and A will be the lowest. So from low to high, we have A, B, D, C. Okay, yeah. And honestly, as long as you clearly label what side is your lowest, what side is your highest, you'll be fine. One is polar and the other is nonpolar. Actually, both molecules are nonpolar. Both molecules are nonpolar. B has polar bonds, but they all cancel out, leaving the molecule without a dipole. So, yep. Yeah, exactly. And Sulai, let's see. That is correct. LD is stronger in larger orbitals. All right, Winnie is a molecule that has polar bonds and symmetric. Let's see. Okay, so if a molecule has polar bonds and is symmetric, it does not have dipole-dipole. For dipole-dipole, you need polar bonds and asymmetry. So you need it to be not symmetric and have polar bonds if you're going to have dipole-dipole forces. Alrighty. Okay. Let's see. I know Jesse asked for a type of problem. Let's see. Best resonance structure with a review. Okay, yes. So when it comes to there we go. The best resonance structure. The best resonance structure will have three things. First, make sure that you have taken care of the octet rule. Second, you want to minimize formal charge. Whoa. And then third, all things being equal, you want to, all things being equal, you want to place negative charges on the most electronegative elements. All right, so those are the three things that you need to get to the best resonance structure. All right, with those in mind, now let's do a problem, and let's do how about this polyatomic ion? All right, so first off, we need to know how many electrons we have to spend. When you find selenium on the periodic table, you'll see that it has 6 electrons. Oxygen also has 6, but we have 4. So 6 times 4 is 24. And then we have our charge of -2, which means we have 2 extra electrons to spend. So we have a total of 32 electrons. Now, selenium is in the fourth period, sorry. So we are going to want it as our central atom because it can break the octet rule. Next step, we need to attach all of our central atoms, all of the other atoms to our central. We've got to make 4 bonds. This is going to take 8 electrons, right? 2 electrons apiece, leaving us with 26 electrons left. Now, we need to give oxygen. Wait, did we need to give oxygen. Wait a minute. I feel like I messed something up somewhere. Oh, well, let's just keep rolling with it. We need to fill out oxygen's octet. Gosh. I actually think that's my neighbor. I think it's my neighbor mowing the lawn. It's the embarrassing moments of a quarantine classes. Am I right? So we've got to give each oxygen needs 6 electrons. We have 4 oxygens in play, so we need to spend 24. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. That's going to leave us with 2 electrons. And now we have 2 electrons left, and we're going to spend those by putting them as a lone pair on our central atom. All right. So we've spent 24 electrons on giving all of our oxygens full octets, and then we had 2 electrons left over. So we so those 2 electrons, 32 minus 8. Oh wait, did I do my math wrong? Let me see. Wait, hang on. Sorry. Let me double check myself. I probably know. Wait, 32 minus 8. Oh, okay. Yes. Okay, awesome. I see my prob. This was an excellent collective catch. Okay, hang on. So let's go back and fix this. 8 minus 32 is 24. All right, and then 24 minus 24 is 0, which means we don't have any electrons left over, so there's no lone pair on selenium. Okay, awesome. Okay, now we're good. All right. So we have filled everyone's octets, but we need to look at our formal charges. When you calculate oxygen's formal charge, when oxygen is neutral, it has 6 electrons. In this structure, you get 1 electron per bond, right? So there's 1. Plus it has all of its lone pairs, 6 in lone pairs. So 6 minus 7 will be -1. And that will be the formal charge for each oxygen on our central atom. All right. Now, let's look at sulfur. Not sulfur. Selenium. Holy moly, what did I do? So selenium, when it's neutral, has 6. But in this structure, it gets 1 electron per bond. So 6 minus 4 is a +2. So selenium has a formal charge of +2. And we know that whenever we have a negative charge and a positive charge next to each other, and we have an atom that's allowed to break the octet rule, we can minimize our formal charge by turning our negative into a multiple bond. All right. So here, if we take one of the lone pairs on oxygen and turn it into a double bond between oxygen and selenium, we reduce the formal charge on that oxygen to 0, and we reduce the formal charge on selenium by 1. So now this oxygen doesn't have any formal charge, and when you calculate the formal charge on selenium, you can see that it's reduced by 1. If we can do it once, we can do it again. We can get another resonance structure with minimized formal charge if we take a lone pair off of another oxygen and turn it into a multiple bond. Now, selenium has no formal charge, and yeah, we can totally do the hybridization practice as well. All right. So this would be our final answer. This would be the best resonance structure because we've minimized formal charges, we've completed our octets, and we have our formal negatives on the most electronegative elements. Excuse me. In this atom, or in this molecule. All right. The hybridization, if we were going to do the hybridization of this compound, because it has 4 electron groups, that means we need to use 4 orbitals for our hybridization. This would be sp3. All right. Yeah, but Sule, I'm guessing you want like a harder example of hybridization, not just what's the hybridization of this guy. We can do that. All right. So, for example, this is totally exam caliber. I could ask you to label the hybridization and determine the total number of sigma and pi bonds in the following molecule. Okay, so I could give you something like this. Oops. Whoa. Oh, hang on. I forgot I can't do stick and line structures because this is a Gen Chem class. Actually, I'm going to change this around. Ah, dang it. Let me change this up too. Here we go. There we go. Okay, so this totally exam caliber label the hybridization of every non-hydrogen atom, and determine the total number of sigma and pi bonds in this molecule. All right. So first, when it comes to labeling the hybridization, remember you're looking at the electron groups in a molecule. So for example, this nitrogen over here has one atom attached and one lone pair. Those are two electron groups. So its hybridization will be sp. Now, when you look at this carbon right next to it, it has two atoms attached, no lone pair, which means that we have two electron groups, which means we're sp hybridized as well. Now, when you look at this carbon here, it has three atoms attached, which means we're sp2. The carbon right above it, three atoms attached. The carbon next to that one has three. The carbon next to that has three. Beneath that one, it has three, and then that one has three. So actually, all the carbons in that ring are sp2 hybridized, because three electron groups each. Whoa, hang on. This one... Oh. Mess up right here. You can't have a carbon with more than 4 bonds. All right, now moving over, this carbon has 3 atoms attached, 3 electron groups, which makes this sp2. This carbon right next to it has 4 atoms attached, so it is sp3 hybridized, same with that carbon below it. All right. When you look at this oxygen over here, which I just underlined in salmon, it has 2 atoms attached and 2 lone pairs. Those are 4 electron groups, so that is also an sp3 hybridized atom. Same with this carbon right here. Now, when we get to the very end, this carbon only has 2 atoms attached, so it is sp hybridized. The carbon next to it, also sp hybridized. And then when you look at the last carbon in this molecule, not labeled, this has 3 atoms attached, which makes it sp2. And then that nitrogen, you'll notice, has 2 atoms attached to it and 1 lone pair. So it is also sp2 hybridized. So there is the hybridization for every atom in this molecule. Yeah, Winnie, that is correct. The other one is not a benzene. That is spots on. All right, so this is the hybridization. Now let's do sigmas and pi's, all right? To do the sigma and pi bonds, to do these sigma and pi bonds, you have to remember that a single, so this is our skeleton key here, is 1 sigma. All right, 1 double is 1 sigma with 1 pi, and 1 triple is 1 sigma together with 2 pi bonds. All right. Now, here's how I count these up. I'm gonna do my my pi bonds first. I find it's really easy to lose track when you're looking at a molecule this big. So I like to put a little hash mark through it physically so I can see it. So for example, there's 1 pi, 2, 3, 4, 5, 6, 7, 8, 9. So in this molecule, we have a total of 9 pi bonds. And then the sigmas, we get 1 sigma in every single bond, 1 sigma in every double bond, and 1 sigma in every triple. So my sigmas will total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. All right. And the hatch marks make sure that I haven't missed anything. So 9 pi bonds and 29 sigma bonds in this molecule. All right, this thing is totally exam caliber. You'll see something like this depending upon the version of the exam that you get. They may be slightly different, but this is an exam caliber hybridization problem. As far as labeling hybridization, determining pi and sigma. All right. Okay, so at this moment in time, we have run our course, at least the course of the. Oh, sorry, that's me stretching of the lecture. So some of you probably are already bouncing to your next classes. My question for you is this: are there any last minute questions before we conclude our last lecture? Fire away. True answer to that question. I have no idea, off the top of my head, what they are. Oh my goodness, excuse me. Sorry, that yawn is definitely the mileage, not the company. I think I finished our exams on Monday, and then I started working on my OChem lab exam, which I'm also giving today. And so that's been the most recent thing in my head is the OChem test, because I was writing it most recently, and now I'm moving on to start working on our final. So I have no idea what the answers to exam 3 are. Wait a minute. That's the best I can do. Let's see. Do you know if you're going to okay, so Raj, great question. I will have no idea until I get there. Once they are, then I can evaluate them, but I have no idea if I'm going to curve at the end of the semester. Okay, what concepts did we not go over today? It's on the test. Here, let me pull up my spreadsheets here. All right, so wait, that's the Chem 420 lab exam. Let's see. The canvas involves quantum numbers, electron configurations, molecular geometries, bond angles, hybridization, intermolecular forces. Covered all of those. The lecture exam has VSEPR, electron configurations, Lewis structures, intermolecular forces, and okay, yeah. So I would say, there are some like periodic trend stuff, aren't there, on the multiple choice exam? So Winnie. Wait, hang on. Boop, boop. So the things that we yeah, totally. The things that we did not cover today. That are on the exam. Things that we did not cover today that are on the exam. Periodic trends. There's a few of those in the multiple choice. Not a lot, but a few of them. And specifically, there's electronegativity. Electronegativity, atomic radius. What was it? Electron affinity and ionization energy. So periodic trends, there's a few of those in the multiple choice. There's also today we didn't do any drawing 3D bonding orbitals. So that's definitely on there. And then we didn't do anything with label, the hydrogen bond, donor, and acceptor. So these are like the three things that are for sure on there that we didn't touch on. Yes, Raj, that is exactly it. Totally. That is the business. Okay, good question. So the multiple choice, whoops, versus take home looks like this. And then the take-home stuff is here and there. The 3D drawing and labeling hydrogen bond donors and acceptors, that I ask you to do on the take-home exam, just because you know, it's easier to just draw them out. But the periodic trend stuff is multiple choice. Let's see. Yeah, totally. Alrighty, so any other questions out there? Oh, let's see. What type of problems? I mean, like, let me just give my memory a refresh. Like, okay. For the periodic trends, which again are multiple choice. These ones are very straightforward. I ask things like, which element is the most electronegative? Or which element is the largest? Oops. No. Hang on. I'm having to reload the live chat. So like for the periodic trend stuff, which one is the largest electronegativity? Which has the smallest atomic radius? That sort of thing. Okay, let's see. Jesse, in the book. Okay, Jesse. Great question. So, so the drawings that I will ask you for are a little more simplified. So, for example, I'll ask you things like this. So I'll ask you to draw the 3D representation of the bonding orbitals between, and then I'll say between for example, between carbon and oxygen in, and then I'll give you a molecule. So the molecules that I give you will not have a bunch of atoms floating around on the turbinus where you've got to draw all of those balloons for everything. I'm just going to tell you to zero in on a couple elements and ask you to draw the three-dimensional representations for those bonding orbitals. So you don't have to worry about these molecules getting huge and having to draw like giant balloon animal pictures for molecules that span forever. It's just going to be tight, narrow, and focused. I believe all of them have like 2 to 3 atoms that you're drawing the bonding orbitals between. So you can rest assured that the questions on the test are very similar to the lecture examples. And then it should just qualify for this problem. I should say for this type of problem. Yeah, totally. So Jesse, they're going to be very, very similar. And not these gigantic beasts. Okay, Winnie, let's see. That'd be something on the take home. Yes, totally. Winnie, this is 100% take home. Material. Not multiple choice at all. Let's see, are there any questions in the multiple choice or take home that require calculations? Diana, great question. There are problems that require counting. You're doing an electron configuration and you have an electron configuration that has 5D electrons, so you have to count your way over across the D block, but that's about as much calculation as you have to do. Or you might have to, for example, we're adding the total valence electrons for a Lewis structure. But but other than like counting or adding the electrons for a Lewis structure, there are no like calculations. Like there's no equations, formula, all that stuff. This is going to be very, very conceptual. The math will the math will come back for the final, but we all get a break for exam 3, which is nice. Yes, exactly. Exam 2 is the evil twin of exam 3. And the final is the parent of them all. Diana, yes. Typically, exam 3 has the highest average. Jesse, great question. Usually I do cover MO theory, but because of the time, we lost to Rona. I had to cut it out. So no MO theory, which does make me sad. Yeah, totally. I think you guys are going to destroy this test. I tried to make it as challenging as I could. There might be a couple tricks in there that you didn't see coming. Some of you, though, may have seen them coming. Sulai, that is a great question. I know. The final will be an even spread from the entire semester. We did not have time to make it there. Nope. So yes, sadly we did not have time to cover colligative properties this semester. We could have tried to push it and force it into today's lecture, but I felt that it'd be a better use of time to answer your guys' questions, your last minute questions before you dive into the third exam. So that's what we ended up rolling with. Let's see. Oh, am I teaching Chem 2 next semester? So Diana, I just recently got my fall assignment, and I'm teaching Chem 400. So you will, so sadly, you won't be able to take me for 401 in the fall. Okay, so Winnie, so I would recommend, I would check out the section in the book on boiling point elevation, and freezing point depression. There are a few equations in that section that you can use to solve the problems on the last exercise. Okay, let's see. Oh, Sulai, thank you. And Diana. Dudes. This is so nice. You are welcome, Winnie. And I gotta be honest. You all are the best Gen Chem class I've ever had. Dudes, I'm gonna miss each and every one of you. I would have so loved to be able to teach 401 because then some of us could have continued to party. The most I can hope for is it's possible that I might be teaching Chem 420 lab in the spring. I have for the past couple of years. So we may not be able to see each other in 401, but maybe we'll be able to throw an after party in an OChem lab in the spring of 2021. Possibly. Assignments haven't gone out for that yet, so I don't know for sure. Dude, I should first I need to get on Discord. It's from what I know, and this is making me sound old, it's basically like a chat server, right? That's Diana. That's my basic question too. I've heard it. I've heard people talk about Discord, and I think that's what it is, but I don't know for sure. Rad. Well, if I did join Discord, if I do join Discord, I'd make it my personal. I'd make it my personal mission. I'd make it my personal mission to say rad more than anyone else on Discord. All right, dudes. Well, I think this is where I'm going to put a pin in this live stream. I've got to go take care of some business, wrap some things up, and get ready to drop my OChem lab exam on my poor students tonight. That's going down at 6 p.m. So, anyways. It has been a good last lecture. I will see all of you or any of you who want to drop by on Friday at 1 p.m. We'll be holding our last office hours. Between now and then, I'm going to try to get some work done on the final so I can maybe give you some concrete information about what to expect, problem distribution, that sort of thing. But until then, I'm going to go relatively dark for the next day and a half. Just like Gandalf, I have to disappear in the mines of Moria, and you've got to figure out how to get to Mordor on your own. But I'll show up later after the exam is done as Gandalf the White to give you that one last push up to Mount Doom to take your Chem 400 final exam. Anyways, it's always a pleasure hanging with you guys. I am pulling for you like the Joker pulls for Batman. I'm wishing you all the best of luck, and I know that you'll be able to crush this exam 3. All right, I'll catch you all on the flip side. Heck yeah. Later.